In this video, we are going to talk about eddy current motoring and braking. Assume that this paper is a metal sheet. Assume that. And also assume that this eraser is a magnet, where I have a north pole on one side and a south pole on the opposite side. So the flux comes out from the north pole, passes round the magnet and enters the south pole. So if I hold this magnet like this, then the flux comes out from the north pole and intersects this metal sheet or this page perpendicularly, goes downwards, and then comes back and enters the south pole. Now I am going to slide this magnet over this metal sheet without touching the metal sheet. I am going to analyze what's going to happen. So the direction of flux here once again is downwards and is perpendicular to this sheet. So let me draw the fluxes with these cross symbols, cross denoting they are going into this through this sheet and away from the viewing direction. And so this is the set of flux entering the sheet, and let me draw more flux near the center as the density of flux drops or falls off from the center towards any of the side. Now let me consider a closed path like this, maybe a circular path, and let me consider what will happen if I slide this magnet towards the right. So that means these flux lines are going to intersect this closed path in this direction towards the right. And now if I consider this point, then the direction of flux is downwards. The motion of this line with respect to or relative to the flux is towards the left, and then the middle finger points downwards in this direction. So that, according to Fleming's right hand rule, will generate an EMF in this direction. Now if I consider this point where again the direction of flux is downwards, the motion of this conductor with respect to the magnet is towards the left, that means the EMF will be generated again downwards like this. That means in this closed path I actually have no resultant or zero resultant EMF, because here I have EMF clockwise, here I have EMF acting counterclockwise, which cancel each other. So there won't be any resultant current ideally. But now let me consider a different path, different closed path, which is like this, and the magnet is here. So now this closed path is not directly under the magnet, but it has some offset towards the right. So that means now here at this point, once again the flux is downwards, the motion of the conductor is towards the left, and that means the EMF will be generated in this direction, downwards. Similarly, once again here also the generated EMF will have the direction like this. However, note that the density of flux is much higher here than compared to here. That means the rate of intersection of flux is much more here than here. So this EMF will be higher than this EMF. So the resulting EMF in this closed path is counterclockwise like this. So that means it will try to drive a current in counterclockwise direction in along this path. Now if the current is in counterclockwise direction, that means it will generate a north pole facing upwards. So this, if you consider this turn or this coil, then the effect of this circulating current is equivalent to a north pole facing towards us. Now, so that means here we have a north pole, and there is a north pole directly under this magnet, and then this north pole under the magnet will repel the north pole here. So this magnet will repel this circuit towards the right. So there will be a net force towards the right acting on this circuit. Similarly, if I consider another circuit which is like this, then once again the direction of EMF generated at this point is downwards. Here again it's downwards, but the flux density being lower here, this will be weaker than the EMF here. So that means the resultant EMF along this circuit will try to drive a current in clockwise direction, which means it will generate a south pole here, and this south pole will be attracted by the north pole directly under this magnet. So in effect there will be a resultant force acting towards the right on this circuit. So both these forces are towards the right. So the net force seems to be towards the right on this metal sheet. If you remember that we actually had moved this magnet towards the right, and the effect was that there was a net resulting force acting on this sheet, which is again towards the right. So that means if I move the magnet towards the right, the sheet or this metal sheet is pulled towards the right, or in other words, the relative motion between the magnet and the metal sheet is tried to be compensated. So the eddy current generated in this metal sheet tries to compensate, tries to move this metal sheet in a direction so that the relative velocity is between this magnet and this sheet is neutralized. So if my if metal sheet is free to move, free to slide, then if I slide this magnet even without touching this sheet, this sheet will be pulled by this magnet towards the motion of the magnet. And this is what is eddy current motoring. Why? Because, say for example, I can I can consider this region of this seat, and then I can put a screw. I can drill a hole through the seat and put a screw through it, so that this portion of the seat is free to rotate around this screw. Then if I slide the magnet over this seat, then it will try to rotate this seat along this anti-clockwise direction. So this is therefore known as eddy current motoring. Similarly, now if I rotate this circular disc, say in clockwise direction, without moving the magnet, that is equivalent to moving the magnet with respect to this metal disc. In other words, the relative velocity of the magnet with respect to the disc is again towards the right. So this magnet will try to pull this disc or rotate this disc in this direction, or in other words, the direction of rotation or the rotation of the disc is opposed by the presence of this magnet. That means if the disc is rotating, then the the stationary magnet will oppose the motion of this disc, which is known as eddy current braking.